Okay, let's revisit our beam problem again. Let's, this time though, assume that we don't need to solve for A. We don't need to find W of X, or our distributed load as a function of X. All we really need to do is solve for B, finding our support reactions. And if that is the case, then we can use composite shapes to solve for this problem. Okay, let's look at this beam again. There's simply supported beam. We know to begin with that we have forces at a y, or a pin, a y and a x, and then by is our roller. But if we look at this shape that we have here, we can look at composite shapes. And if you look in the back of your book, you will see that it looks kind of like a triangle, and it also kind of looks like a rectangle. So let's split it into these two shapes. So here I have the two shapes. The pink one is this rectangular shape on the bottom, and the green one is the triangular shape on the top. What I want to do is find out what this force is. I'll call this F1. And then the green force over here somewhere, it will be as F2. To solve for those, it's very easy. It's just like integrating it, but because they're simple composite shapes, F1 is really just the area of that rectangle, right? So we have 200 Newton meters is the height of that triangle, newtons per meter. And the length is 6 meters, we end up with 1,200 newtons. Then for F2, our green one, it is a triangle. And the area of a triangle is 1/2 base times height. And our base is, again, 6 meters. Now the height we need to be careful of. The height for this is, this distance here. And if we look at that distance, that is going from 200 to 400, or it will be 200 newtons per meter. Be very careful with that. A lot of people won't use that 200 newtons per meter. They will use 400 newtons per meter. But it really is 200 newtons per meter. And this comes out to a value of 600 newtons. So let's redraw our free body diagram for this. Okay, so if we look at this, we have our forces on here, our free body diagram. We need to find out where that 1,200 newtons is. We know for this shape, right, it's a rectangle, the center of it, or the centroid, is right at the center of this, or at 3 meters. That's our F1 is at 3 meters. So this is 3 meters. For F2, it is a triangle. And this is our 600 newtons, or F2 we had. And that is 1/3 the base, or we could do 2/3 to the other side of our base. So if we figure that out, it is 6 meters across, so 2/3 of 6 meters is equal to 4 meters. Okay, so there we have it. It's at 4 meters. Now we're back to our nice, easy free body diagram and solving these types of problems, right? We know by looking at this, we can sum forces in the x direction equals 0. We know then that AX equals 0. If we sum our moments at A equals 0, we will have our negative 1,200 newtons times 3 meters minus 600 newtons times 4 meters. And last, we have plus By times 6 meters. That's this whole length here is 6 meters. Okay, so when we find our value for By, we come up with 1,000 meters. And then the last step is to sum forces in the y direction equals 0. And if we do that, we have 1,000 newtons, which we just calculated for By, minus our 1,200 newtons, minus our 600 newtons, plus AY. Solving for AY, we get AY equals 800 newtons. And there we go. That is the way to solve this problem using composite shapes.